So the second piece of calculus is being able to take the derivative backwards. So to be able to take something and answer what function generated this particular derivative. So if I were to give you an example, a function like this, 2x. Okay. What function has 2x as its derivative? So I'm going to give you some notation here just to show how to write that. The way you would phrase this question in symbols is to take the thing that you're trying to underivative and you put this fancy stylized s in front of it and then a d and whatever your variable happens to be. So this set of symbols here, it's S for summation, and when we get to the area of curves section, I'll be able to maybe talk you through why it's a big S for summation. For now, all you need to be able to do is recognize that this giant stylized S with a dx at the back is asking you what function has this thing here, as its derivative. So at first, we're just going to be doing some guessing, right? Well, educated guessing. I have a function here. I have 2x. So an x comes from an x squared, right? Like if you take the derivative of x squared, the 2 comes in front, and then you drop the exponent by 1, and well, there you go. That's the thing that we were after. So the answer for this here, what function has 2x as its derivative, would be x squared. Now there's one extra little wrinkle that we need to consider, that x squared gives me the 2x, but I could have, let's say, a plus 5 back here. Because if I were to take the derivative of this, the derivative of x squared is 2x, and the derivative of 5 is gone. Well, that would also be true if it were 15. It would also be true if it were 153. It would also be true if it was 153 pi, or 153 pi over 8. Right? It doesn't matter what this thing is back here, as long as it's just a number. So what I'm going to write in there is, instead of picking a number at random, I'm going to put in a little placeholder for a constant, just some number. So plus c. Let me fix my plus sign there. Okay, so c is just, oh, looks like my yellow is expired. So c is just any constant value, which is just a number. Now, there will come a time when you're doing an application where you need a specific number there, but that's based on the context of the problem. So since we're just undoing the derivative here, there is no context for the problem, so we're just going to tack this number on the back to acknowledge that it could be there, and that we might have to figure it out later when it's time for applications. So this should be pretty straightforward. I'm just using this video on this topic as an introduction to the notation and the idea that we're trying to undo derivatives. So the next example we'll try then would be the integral of 1 over x dx. So in English, this says summation of this thing multiplied by this little wedge. But what it's asking me to do is, what function has 1 over x as its derivative? So you go back through the catalog and you try and remember which function gives you 1 over x as its derivative, and the answer is ln x. So the derivative of ln is 1 over the argument, which is what I have here. And I need to acknowledge that there may be some number at the back that will have to be determined later, based on the context of the problem I'm trying to solve. And that's it, right? Look at this thing. Tell me what function has that as its derivative. That's all we're doing in this particular video. So, next one. What is the integral of 1 over 2 root x? So the question there in English is, what function has 1 over 2 root x as its derivative? And if you think about that, that's 1 over 2 x to the 1/2. That's 1 over 2 x to the negative 1/2. And I could get this as a derivative if I started with x to the 1/2. Bring the half in front, subtract 1 from that. So the answer must be x to the 1/2 plus c. That's just power rule going in reverse. And of course, if you prefer the other notation, you will recognize x to the 1/2 as the square root function, with this random number to be determined later tacked on the back. All right. So I'm going to erase these, and then we're going to try a moderately more complicated one where I have to futz about having coefficients in front in order to make the derivatives work out. So this one, which function has x to the exponent 4 as its derivative, has a tiny little wrinkle in it. It's not too complicated, you just have to do some thinking. If I'm trying to get an x to the power 4 as my derivative, it had to have come from an x to the 5. That's the only thing that generates that, right? If you start with x to the 5, then the derivative would be 5x to the 4. And that's the piece I'm after. I want this. So that's good. The thing I don't want is this 5 in front. Okay, there's no 5 in my integral here. So I need to modify this thing I started with in order to eliminate this 5. And the way you eliminate a multiplication by 5 is divide by 1. So if this were here, then I'd have 5 canceling 5, which would leave me with x4, and that's what I'm after. So I need to introduce a division by 5 into my starting point. So just to check what you've done, if you take x to the 5 over 5, that's the same as 1/5 x to the 5, and you add your constant. If that was the function you were working with, the derivative of that thing would be 1/5. Bring the 5 in front, reduce the exponent by 1. The derivative of a constant is gone. 5 times 1/5 is 1. They eliminate each other, and the only thing I'm left with is x to the 4, which is what I was after. So what I've just figured out then, with all that work there, is that the integral of x to the 4 by dx has to be 1/5 of x to the 5 plus c. That 1/5 there is going to balance out the exponent that pops in front, leaving a coefficient of 1 in front of my function. And this number, which we will have to determine later based on the context of the problem we're solving, just vanishes because the derivative of any constant is 0. All right, so it's a bit of reverse engineering, right? You take a look at the function you're trying to get. You think of the base function that generates this as a derivative, and then you tweak the coefficient in front in order to make sure it matches the number in front here. So let's erase this and we'll give another one a try. So I'm trying to solve the integral of a power 5. It's just a polynomial. So I'm going to be able to go through and do these piece by piece, right? If I was doing a derivative, I'd do the derivative of that, and then add the derivative of that, and add the derivative of that. So the integral works the same way. I can integrate it piece by piece, as long as these pieces are separated by additions and subtractions. If they're separated with multiplications or divisions, I'm going to have to start using the, I'm going to have to undo product rule, or I'm going to have to undo chain rule, which is a touch more complicated. For right now, anything that's separated by pluses or minuses doesn't require that level of detail, so we can just do it piece by piece. So I'm just going to try and do this straight up without doing too much back talk about it. So if I was trying to generate an x to the 5 as my derivative, x to the 5's only come from x to the 6's. To generate an x squared, I need to have come from an x cubed. To come from an x, I needed to come from an x squared. To come to a number with no x attached, I had to have come from an x. And then there'll be any number of constants attached at the back. So this is the basic scaffolding for the integral I'm trying to solve. A handy way to figure out the coefficients is if you just go through and you take the derivative of this basic structure and then you adjust the coefficients accordingly. So if I take the derivative of my scaffolding, let me write that down, take derivative of scaffold. So this would be 6x to the 5. This would be 3x squared. This would be 2x. This would be 1. And this would be gone. So now I'm going to look at the coefficients that my scaffolding is generating. And I'm going to look at the coefficients that I want to show up. And I'm going to adjust this accordingly in order to make it work out. So in front, x to the 6 generates the x to the 5 that I want, but it leaves a 6 in front that I don't want. So how do you get rid of a multiplication by 6? Well, you divide by 6. So I'm going to need to park that in front there. On my next one, this x cubed is going to generate the x squared that I need, but it leaves a 3 in front. I don't want a 3, I want a 4. So I'm going to have to eliminate that 3. And I'm going to have to put a 4 in its place. So if you look at this, right, 3 divided by 3 is gone. 4 times x squared gives me 4x squared, and that's what I'm after. The x squared is giving me the x that I want. That's good. But it's leaving 2 here as the coefficient, and I want 6. So that's not enough. So I could just, I mean, if you want to be methodical about it, right, I could divide by 2 and then multiply by 6. That will do. So that's multiply by 6, divide by 2. You may spot, though, that 6 divided by 2 is just 3. I'll save you some pencil strokes. The x here generated a term without an x attached, which is what I wanted, but it's given me a 1, not a negative 4. So I'm going to have to not only quadruple that number, but I'm going to have to change the sign. I'm going to need a negative 4 in front of that. This constant can be anything I like. This was positive, this was positive, so I should have done it now. So if this was my function, the derivative of the first term would be 1/6 of 6x5, and if I divide those two things out, I'm left with x to the 5, which is what I'm supposed to have. 4/3 x cubed, drop the 3 in front, it eliminates the third in the bottom, 4x squared is what I'm after. This one would be, if I actually use the 3, would be 3 times 2x, 3 times 2x is 6x. That's what I'm after. Derivative of x is 1. Negative 4 times 1 is negative 4. And the derivative of this constant, whatever it is, just vanishes. So what I've got there is that the integral of x to the 5 plus 4x squared plus 6x minus 4 must be this. This is the function, or the family of functions, because this is a list, right? This is the family of functions that have that as its derivative. Okay, so here, this one's a bit dirty. This thing here, cos squared x, that means cos x squared. So that's a function in a function, which means that this thing had to have come from chain rule at some point. And maybe you don't want to do that quite yet. I don't think we're quite ready for it. So when you look at that, if you see chain rule, it's going to require some more complicated techniques in order to solve. So instead of doing it that way, I'm going to rack my brain for something that 2 cos squared x minus 1 can be replaced with. And if you think about it for just a little minute, 2 cos squared x minus 1 is one of the double angle identities. That's the same as cosine of 2x. So I'm going to make that replacement because that has eliminated my chain rule. I mean, it's still there a little bit, but the thing in the middle has a pretty simple derivative. So I'm going to make that replacement here. Get rid of this thing because it's in my way. Integrating this function is the same as integrating cos 2x dx. So you may be starting to figure this out when you were in advanced functions and when you were in grade 11 math and you were doing all of these trig identities and you were wondering why on earth would I ever need to know these? Well, this is why. Being able to flip-flop between complicated cosine or sine expressions into something that's a little easier to work with for calculus can make your life a bit easier. So once I make that substitution, right, I don't have to worry about getting something from a chain rule. I just have to know what generates cosine as its derivative. And the only thing that does that is sine. So I'm going to start with my infrastructure here. So what makes cos of 2x? Well, sine of 2x makes that. So I'm going to do the derivative of my scaffolding here, right? Like this is my first guess, and that might be it, right? This might be the answer. So I'm just gonna check it by take the derivative. Take derivative to check. So the derivative of sine is a cosine, but this is a chain rule. It's a function in a function. So I need the derivative of the outer layer, and then I need a derivative of the inner layer. So the derivative of 2x is 2. That would, if I rearrange things, give me 2 cosine of 2x. And that's very close to what I want. It's just too big by a coefficient in front. So we're going to use the same technique as we did in the last example. I'm going to take this thing and I'm going to introduce a division by 2 so that this divides out this and leaves me with cosine of 2x, which is the function I was trying to integrate in the first place. So that's good. So what I figured out then is that 1/2 of sine 2x is the function that gives me cosine 2x as its derivative. So the integral of cos 2x must be 1/2 sine 2x. Like that's how it works. The only thing I need to finish her off is to clean up this mess so that I don't have to look at it anymore. And remind myself that this function could have any constant I like tacked on the back, and it would still have the correct answer. So if you get into the problem sets, you're going to be hunting for basic derivatives. So you're going to look at this thing in the integrand, and you're going to ask yourself, what would make this as its derivative? Once you've done that, you've come up with the basic function. You're going to have to tweak the coefficients in front to make sure that you end up with the correct number here. You're going to have to remember to tack a C on the end. If you see something spicy like this, you might want to consider doing a trigonometric substitution. But basically, it's just hunting for the basic derivatives. Good luck.